welcome to another episode of Darko's Game Dev Cookbook. I'm finally back with my ray tracing tutorial. So it's been a while since we did this, and I don't know, maybe 2 months or something like that. And in the last tutorial I said that we're gonna be covering something called Fresnel, which will enable us to do some reflection/refraction magic. And we will be doing that, but we will not be doing that in this tutorial. As the time passed, I think it's finally time for us to step back a bit and redo the things we have right now, redo them again in a good way. So let's take whatever we had before and all the knowledge you built so far, which should be a lot of things. Let's take that and let's try to make a new ray tracer, which is gonna be doing pretty much the same thing as the old one did. What we're gonna do it in a way so that the code makes more sense, and we're also gonna be covering the ray tracing loop that is quite important for the whole ray tracing logic. And once we do that, and once we get this beautiful scene you can see on your screens right now, once we have it, then we can actually start with the Fresnel thing I mentioned. And Fresnel itself, it's a pretty small area, but it's in this context and in the context of this new ray tracer, it will add a lot of value. And then we can finally start playing with different kinds of objects that are either translucent or they're opaque and so on. And we're gonna start playing with some textures as well finally. Yeah, and that's about it. So the thing you see on your screen right now, it's the thing I made real quick, and it's that new version of it. So if you don't want to go through the whole thing with me right now, that's fine. I'm happy if you can just go into the code and figure it out yourself. The link is down below in the description, so feel free to go there and check it out. If you do want to learn how each of the chunks of the code work, then stay tuned for sure. The thing that I will cover here, besides the obvious loop that we're going to be adding and obvious refactoring that we're going to be doing, I will also be adding ray plane intersection. So you can see here that we have a bunch of planes, 5 of them in total, actually 6, one is even behind the camera. And we're going to be adding those planes around. So we're not going to be having that cube map, we're going to have the planes just for the fun of it. And this is the end product we will get in this tutorial. And then in the next one, we'll hopefully be adding Fresnel and other cool stuff. But this is a pretty good base for us to get started, pretty much. Yes. Okay, so let's get into it. I'll just start a new shader. Let's do it from scratch. I will be copying the pieces of code that doesn't need any special refactoring. I will just be copying it from the last shader. We don't need to go through it all again. You should know the basics right now. If you don't know, just go back to the first lesson and you're good. So let's copy, let me see. Yes, so for our scene we're gonna need things like lights, cameras, or actually I can do it here so you can see what I'm doing. So first thing, we definitely need to fix the aspect ratio, and in one of the tutorials I already did, we are fixing the aspect ratio, and this we can just copy this one and let's carry it out here. So our UV coordinates go from minus 0.5 to 0.5. So this is minus 0.5x, 0.5x, so minus 0.5, 0.5, and y goes from minus 0.5 on top and 0.5 on the bottom. Once I do this and then compile, I'll get pretty much similar situation as we had before, but obviously the aspect ratio is different, so you can see that the color gradation is slightly different. Okay, but let's start thinking about things. So the first thing we need is obviously the camera, and I will just copy the camera structure we had. We might change it slightly, and I don't strictly remember if this was the last version we had. This might have been named slightly differently, no worries, it's still the same logic. So we have the camera position, and then we have the focal distance, which is the distance between your camera and the canvas, if you remember. So we're gonna place this camera over here. We're gonna do now it's not instantiated, of course, so the struct itself is defined, but we need to instantiate it. We can, as I said before, we can do it in many different ways, but if you remember, we had this setup scene function before. We don't need to have that. We're gonna have that function as well now, but the camera itself, well, we're not gonna be doing much with it. We might be moving it around and such, but it doesn't matter. We can still, for now, have it here because it's not gonna move, and we're gonna say, well, the camera is pretty much here and it's not moving anywhere. We're gonna cover camera rotations and movements later on when we actually want to do rotations. I need to go through rotations first, so you can actually know what's happening when I'm doing it. So we're gonna instantiate the camera like this. It's a global thingy. I can even make it const, and I say, yeah, the position is 0, 0, and then on Z we go minus 0.3. It might also be that in the previous series or the previous retracer we had Z that was positive. We had maybe left or right handed system, and here we're doing the opposite, so don't be worried. For now, let's just say that the negative Z is going towards us, positive Z is going towards the screen. So this means that we are at 0.3, and if there is an object on 0, we should see it. If there's an object on 0.6, it's behind the camera. We can't see it. Simple as that. So the camera is instantiated, and we have the position and focal distance. And we're gonna, let me see what we need to do. So to be able to draw anything, of course, we need to have the sphere. So maybe let's start with the simple sphere we had before. I'm gonna copy a chunk of code I have in the new version over here, and here I put two spheres. So this is the way you can instantiate multiple objects, or actually this is the way you can instantiate a single object as well. So if I did this, then that would mean that this instance is alive pretty much. But we can do this, and then we can tweak each of these instances individually however we want it. And usually what you can do right now, you instantiate one, instantiate the other, and just say, well, sphere 0 equals that sphere. Like, you can do whatever you want. Those are maybe details you should not be caring about at this point. Then we're gonna do the setup scene thingy. The reason for that is simple. We gotta set the values of these spheres, or maybe let's do something different. Let's try doing something different. I'm gonna say that we have, and also one more important thing is that I added this material. So maybe for now let's ignore the material part, and let's just have the position, color, and radius like we had before, if you remember. So let's say we do have two spheres. Why not? Let's step up our game a bit, and let's say that the sphere, we have this sphere, we're gonna call it sphere 1, and that's gonna be a sphere something. This syntax, if you're not familiar with GLSL that much, it's just a regular constructor that takes arguments that correspond to these arguments over here. So if you start passing things over here, they will go sequentially in the same way as you have the fields inside of the sphere structure. So the first thing obviously needs to be a vector of position, then you have the color, and then you have the float that it's a radius. So let's break it down a bit. So I'm gonna say that the position of the sphere, well, it's the first sphere, so we're gonna have two of them, obviously. And let's place them, or actually I'm just gonna use the positions that worked for me here, so we don't need to change them. So let's say that this is the first position of the first sphere. Then the color, I choose a reddish one, or actually this is the bluish one. So but maybe, yeah, let's put this as the blue one, and let's put the radius to 0.08. I mean, these values, depending on how you make this implementation, they will definitely be different. In your case, it might happen that the sphere is too big or too small. Tweak it as you want. It's up to you pretty much. So we're gonna copy this thing and we're gonna make another sphere. By the way, I seem to be having a command that's not necessary, so I'm gonna do this. And I'm gonna name it sphere 2. And I'm gonna move my mic a bit. Let's do it like this. And now we have 2 spheres, but they're not. We want to put them in this array maybe, but let's do the array part later on. So for now, let's act that we have one sphere. So we're going to use this sphere 1 in our intersection code. So what did we say before? The heart of each ray tracer is this intersect or ray trace or ray march, or call it whatever, function that basically, oh, I also hate these. The function that goes through each pixel, in this case, it will go through each pixel of your screen. So depending on your resolution, you might have more or less pixels in this implementation. It will go through each pixel and then intersect through each pixel in the scene. So if you're not familiar with this concept, then you're definitely watching the wrong episode of this tutorial. Just go back to episode 1 and watch that one. You can potentially skip the rest if you don't want to fiddle a lot with some specific things, but definitely you need to check that out first. You won't understand pretty much most of the things I will be doing right now if you don't do so. Okay, so let's see what I wrote here. Yes, so the main code is going to be a ray march function that will go through each pixel. And for that, we got to have a, let's make it void, and we'll see what kind of a function we need. Let me bring this window on the other side so it's a bit easier. Yeah. So ray trace window management is not happy today. Ray trace is gonna have a something. It's gonna have a direction in which you are shooting the ray, so you should know this already. And then you have the in vector 3 ray origin, which is gonna be, in our case, it's gonna be the camera position, but it might be anything really. If you want to change the logic, maybe have multiple cameras so you pass a different camera position, something like that. The ray marching or ray tracing function should actually return the final color we want to display here. So I'm just gonna put temporarily, we can move this here, so this one returns the color, and then we can put vector 3 here. And then let's do the dummy part. We're gonna do ray direction equals something, I don't know, 0, 0, 1. Direction always needs to be normalized, or else the math won't fit, as you already know. Ray origin is gonna be camera, which is should be instantiated at top. Camera dot position, right? Yes. And let me see. Yes, of course, we're not returning the value. Yes, when you see a bunch of these errors, I'm gonna actually just kill this one and return a, let's say we return just a pure white color. Or let's make it black so it doesn't flash too much. Something slightly gray, maybe. Okay, when you see a bunch of errors, don't get discouraged. Just do your stuff. Ray direction, dimension mismatch. This is vector 3, of course. We need to specify this is vector 3, so it's a constructor of this one, and then here like the style I use for coding is I always put space after comma, and you'll notice that in many cases in this code you will see either this thing, which is for some reason I just can't stand that format. I'm used to different formats than that one. Maybe that's your style, but I haven't seen that style that much, to be frank. I saw it, one person in my life used it pretty much so far, and it was a bit weird. And of course this is not really what we want, so we can say vector 3 final color. You can call it whatever you want, and we do ray trace, ray direction, ray origin. I hope my keyboard won't sound super loud on the recording. If it does, I'm sorry. Your ears will need to suffer a bit, I guess. Okay, and now we get the color. That's nothing, right? It's just gray color. We're not doing anything yet. The thing we gotta do in ray tracing, we need to intersect our sphere with something. And I also did something that I like in this chunk of code, because it's a lot of, it will be a lot of lines of code in one file, and let's just do this so we can easily separate it and easily browse through code later. The camera, let's also split the arguments a bit, and let's maybe, yeah, this is okay. Cool. Let me see if the recording looks okay. It seems fine. Maybe the format of the picture is not perfect, but I guess it's fine. Yeah, it's cool. What else? Now we gotta start intersecting, or actually, before we start intersecting, we gotta do the camera dance thing we did before. So right now, your ray direction is just going straight. So for each pixel in your canvas, it will go straight. We need to tweak it. You remember how we did it before, and I will just replicate that behavior to some extent. We're gonna say that the, yeah, exactly. Let's calculate the canvas position, as we call it. In theory, the canvas position, as we call it, it's actually near clipping plane. And the thing you see, there can also be a far clipping plane, which actually, I think the easiest way to do this is basically doing whatever you would like, you will be doing when you start doing these things. So whenever you don't know something, open up Google and type whatever you want. There is, at least regarding ray tracing, there's so many materials, you will never be lost. So make sure to use Google and use materials and read through materials a lot. I will suggest one more page in just a second that I really like. It's simple and contains pretty much everything you need for this. The near clipping plane. This, can I open a larger version of this photo maybe? Not super helpful, but I can zoom in, or maybe just use a different image. So yeah, near clipping plane, this is your camera over here. This is the so-called canvas. The reason I called it canvas is you are kind of using it as a canvas. You are going with a ray through the canvas and hitting something, right? And whatever you end up hitting, you paint it on this big thing. So you are making a canvas. You are painting on the canvas, but it's actually near clipping plane. What does that mean? Well, that means that in theory, whatever is between the camera and this plane over here will not be displayed, and whatever is behind it or further from the near clipping plane should be shown on your screen to some extent. There's also this far clipping plane, and we are not using this far clipping plane here. Far clipping plane is important because of, I mean, performance. You can reduce your frustum drastically, and you can make things not render if you want to, because the clipping plane, that's the far clipping plane, will clip them out. So they will be culled in a way, and then you only see what's between these two. For in this scenario, our far clipping plane would actually be one of the planes we will render for real. So if you check what I did here, it's basically gonna be this one. That's our kind of far clipping plane. But just so you know, there is two of these. So I would like to change the naming slightly, since we use the canvas, and we can use the clipping plane or clip plane, whatever you like, since we only have one, and we can calculate the position of that clip plane. And we can do that by taking the camera position and adding the focal distance. But there is also a catch. That's not the final equation, right? So you gotta take into the consideration where on that clipping plane you are based on these coordinates. So in theory, what you just need to do is, I think we did the same thing in the previous ray tracer. You take the UVX and UVY, which is gonna be the coordinate on this thing over here. It's basically our screen is gonna be the near clipping plane, and then you say, well, I have the X coordinate, I have the Y coordinate of this plane, and of course this calculation only works if you are looking straight and your camera is looking down the Z axis. It won't work in any other cases, obviously, because your X and Y are then not just pure X and Y from this this screen over here. It's definitely going to be different, and we will cover that when in rotations. So for now, let's just look down the Z axis, and let's say that the Z axis is actually camera.position.z. And on top of that, we need to add the focal distance. Where is our focal distance aiming towards? Where is this clipping plane? Obviously in front of the camera. But what is in front of the camera right now? Well, in front of the camera we have, if our camera is on minus something, it's on minus 0.3. We said, well, whatever is in front of us should be more positive, right? So we can place it, if our focal distance is like maybe 0.1 or 0.6 in this case, this means that we need to add this 0.6 on top of this to get the real focal distance, or not the focal distance, but to get the Z position of the clip plane. So we're gonna say camera.position.focal distance. Let's try compiling it, and of course we gotta add this again. Illegal vector field selection. Sorry, this. So when we have this position, we can calculate the ray direction. Why? Because this is just the position in 3D space, and our direction should be, in theory, taking this clip plane position and deducing the camera position from it, and then we have this directional vector that's going towards a specific pixel on this clip plane. So we're gonna say vector 3 ray direction is equal to, we're gonna normalize it, of course. As soon as you type direction, always have in the back of your mind, always know that whatever the output here is, it needs to be normalized. Why? Because the direction doesn't have a magnitude. It should never ever have a magnitude. If you do have a magnitude, then you have a normal, like you have a vector of some kind you want to deal with. If you have a direction, you always have a normalized vector. So be careful about it, because if you are doing dot products or any other sorts of calculations with this vector that is not normalized, you're gonna have a really bad time, and it will take you a while to actually figure out that you have a bug. So we're gonna do clip plane position minus camera.position, ray direction redefinition, of course, because we faked this one before, and now our ray direction is done. And what we need to do now to get the we don't need this, we can pass this directly. To get the ray trace called correctly, we need to do we are already doing it right here, but we're gonna pass the ray direction, and ray origin is gonna be the camera position, which will now change nothing, because obviously our ray tracing function is not doing anything in particular at this point. But we're going to make sure that we actually do something here. So to start with, we need to do a intersect sphere call, and I'm looking at the old material from the last series of tutorials. And we're gonna bring that sphere intersection function over. Again, if you don't know what this chunk of code does, I already covered this in the first tutorial, so go back and watch it. If you know what this does, or you simply don't care at this point and you want to see how the rest of the ray tracing works, then be my guest to do it. But I think it's quite useful for you to know what this does. So we need our intersect sphere, our magical function that checks if your ray is intersecting a sphere. And of course, since that function is using a quadratic function to actually get the intersection, we're gonna paste our utils function that we also had in that last old ray tracing implementation. And with this, let's just try. I like to hit compile just to see that something didn't go wrong with pasting. Awesome. Let me see. So this will now be something like this. We're gonna first write a super simple implementation of it, and then we're gonna broaden it up a bit. And so we're gonna do intersect sphere, something like this. If you do intersect in this sphere, then make sure to return the color of that sphere. That would be like the basic implementation we did in the first few minutes of the first tutorial. Let me see. So if we do the intersect, yeah, exactly. And this does the, I'm just looking at some color calculation. I'm trying to figure out what's the easiest way to actually reproduce whatever I did here is, so you don't get too confused. Yes, we can do, for a start, we can do this, and then we can just slowly start expanding it. So the intersect sphere, if you remember, takes the origin of the ray, takes the direction of the ray. We have both. Check, check, perfect. It takes the sphere, and the sphere itself is gonna be the sphere you're trying to intersect with, basically. The distance, all of these are out. You can also indicate, by the way, that all of these are input only. There's also in-out option you can add, but these indicate these are input. And yes, I'm gonna just do this. Maybe we can instantiate the final color like this. Equals after 3. Okay, so we gotta do the origin. Origin is gonna be ray origin. We gotta do the direction, which is gonna be ray direction. And then we gotta pass a sphere. In this case, we can use sphere 1. We're gonna make a for loop here, by the way, so we can intersect with multiple spheres. And then we're gonna do distance is an out variable, so we're gonna define it here. We're gonna name it dist because distance might be a keyword. Then we're gonna, what else? We have the surface normal. Surface normal, if you remember, is the normal that goes from the surface that you hit. So you know the angle of that surface, kind of. So we're gonna do this. Surface normal. We don't need to set it to anything, I guess. It's not really that important. And then we can also have the vector 3 p hit. Or actually, since everything is like this, let's make it p hit. And then let's pass them. So we have distance, we have surface normal, and then we have p hit like this. So you say if you intersected that, then we can return, or actually just set the final color to sphere 1. Color and now we might get the sphere, and we get the sphere. Of course, it's not lit right now. So we can choose to either do the lighting first, or we can choose to handle multiple shapes first. I would like to tackle the multiple shapes parts first. So for doing that, I'll copy this small for loop we have over here. And the for loop looks pretty much the same as in C++, no difference whatsoever. And we have two spheres. This is like, now it's kind of hard coded. We can change it later. For now, we'll have two spheres, so we don't really care. And here we can say that we're gonna have something called spheres, and we're gonna pass the eye here, so we go through both of them, and then we can intersect both of them in one go, kind of. But there is a catch. This one doesn't have these spheres. Try setting these spheres up. Since we're gonna do some tweaking with our scene elements, we're gonna do if you remember, the good old setup scene function, and then here we're gonna set these guys up. So we can say spheres 0 equals sphere 1. Also, this is the part we're gonna be fixing along the way. We're gonna make it a bit more generic at some point. For now, it's fine. And setup scene, maybe I'm thinking maybe we could extract it. No, let's keep it like this. So now we have spheres 0 and 1. If I compile that, nothing happens. Let's see why nothing happens. So these are defined. Of course, yes, we're not calling this function. So we're gonna call this function here. And we have only one of them. The reason for, or actually we do have two of them, but we don't see both of them. So I'm gonna use the position I used for this new one. Let's do, actually it's kind of mirrored on the other side, so it's minus 0.12. The color I use for the other one is red, has a reddish flavor to it. So let's put the red one. What did I do now? Sphere 0, 0, and yeah, okay, and this one as well. Spheres, okay, and now we have two spheres. They don't have proper color or lightning, and that's fine. Let's add let's start adding color. And if you remember the last time we did this, we used Fong shading as a basing lightning model. We're gonna do the same thing, so I'm gonna copy and paste pretty much the logic we had there. The only difference I made in the meantime is that I used a slightly improved version of it, which uses this halfway direction, which prevents some weird light behaviors. When the light is super close, it can get quite weird. But in the gist of it that I explained, I don't know which tutorial that was, maybe third or second. I'll leave a link somewhere on the screen, hopefully. Go there and check it out. We're gonna use the same logic for lightning, and I will not be rewriting it right now. So let's put that somewhere. So we have the intersection code, utils, maybe let's put it here, and you also have this lightning color block. Yes, so there is no difference between this algorithm and the one we did before. It's pretty much the same, but the thing that we are missing in this current implementation to be able to do this is we are missing the light. Obviously, we can't light the object without any light in the scene, right? So we can make a struct point light, and we're gonna make in our implementation, I would go for only one light for now. Actually, I'm just gonna do the same thing as I did here. So I pasted this structure. So it has a position and it has a color. This one, not used for now. I was kind of lazy to do it, to be frank. And there is one light. and I just prepared this to be able to support multiple lights in the future, but you don't need to do it. You can just do something like this light, or you do the instantiation like we did here. But for now, let's just act like, let me see how I did it in this scenario. Yeah, classical, as we did with the spheres. So I'm gonna take lights 0, so the first and the only element in this array. It is going to be something, and we can take the instantiation I had here. I also put some comments on the side so I know which field is what. We're going to fix this system hopefully in the future when I want to do it. For now, let's focus on the fun things first. Light 1. Okay, and then we are going to have another requirement. I'm gonna get to that point in just a moment. So we have the light now, so you can get the functioning as we did before. The only thing that's missing right now is the material, and we had the material in the functioning implementation as well, so we can pretty much copy that entirely. So material as a structure, I'll copy it from the old one, and it looks the same as it did before. There is no difference whatsoever. I'm gonna have 2 materials for now. And we're gonna be using only one for spheres, I guess. And then when we add the planes, we're gonna just add another material to the planes. And then let's instantiate. I have some cool numbers over here that seem to be working fine with this setup, so I'm gonna be using that so I don't waste anyone's time. We have 2 materials that have different kinds of props. Again, if you don't understand what these are, just go back to one of the previous tutorials where I explained functioning. And then we have the materials defined here, and we need to place these materials to the array structure the same way we did before. Or do we need to do that? We actually don't need to do that because we're gonna set the materials directly on the sphere. So let's kick this out, and let's put this material back that I uncommented when we started, and we can also move the material as something that's super generic on top, possibly here like this, and then this one is now lacking the material definition, so we're gonna do material 1, or however I called it. Yes, I don't have them defined, of course. I'm gonna define them just here below. And here we're gonna do material 2. These over here, they need to be const because you can't set them on the sphere over here if they're not a const value. Just so you know, information bits for you. So this is not used for now. We're gonna tab it a bit, or no, it's better like this. Setting up the scene. We have the spheres, we have the lights. Check. That all looks good. We are compiling now because all of the types we are using all over the place are in place. And now we're gonna figure out how we get the real thing out of this. Let's try to plug the lightning code back so we don't get just the plain color, so we actually get the light color. Where did I place the light? Here, I pasted this one. Yeah, so the light seems to be slightly in front of the camera, so it's minus 0.2, and the Y position is slightly above the camera, and spheres are located on minus 0.05. Is this the location, or yeah, it's the position. Color, radius is okay, so they should be lit from the top. Yes. And let's make it happen. So the final color we're gonna have here is not gonna be the just the plain sphere color, but we're gonna try to get the lit color instead. The way we do it, we're just gonna call the get lit color distance, so we can push that out instead. Let's try doing this primitive thing before we actually do it in a proper way. So we're gonna do the get lit color, the origin, So, or actually no, sorry, it's view direction, then surface point position. This is a bit hard without IntelliSense or anything like that, to be frank. So I'm just gonna paste it here temporarily, so we get whatever values we need to see. Get lit color needs to be view direction, which is gonna be ray direction. Also, one of the things you can definitely do, like I named it view direction, we could actually rename it to ray direction, make it better, but for now I'll keep it. I definitely encourage you to do it. Surface normal. Surface point position, sorry, that surface point position should be the P hit position that we retrieve from this one. The object color should be spheres. Also, I encourage you to change the signature of these functions if they make sense in some other format for you. That's completely fine, even better if you do it. Point light is our lights for now. We're gonna be using only one light from lights 0. Surface normal. By the way, is this? Yeah, this is in surface normal, so it's not changing it or anything like that. So we can pass our normal surface normal, and the material is gonna be, for example, when I said change the signature, you could have just passed the spheres instead of the sphere color and material separately, but it's just the way how things developed from the first tutorial up until now that we have this structure. But you can choose to do that instead, or actually let's do that immediately. So we're gonna pass the spheres I here, and then I guess we can change the implementation of our function over here. Maybe it's better if we tackle these things now then later. So this is the one we are changing, sphere. Get lit color. Oh yeah, now I remember. Okay, so this is not a generic function. So the way I split it, the reason why I split it is because we're not only intersecting spheres, we're also intersecting we're intersecting planes, and we'll tackle that, the generic part as well, hopefully again in the future. I don't want to confuse more at this point. And this is gonna be, as I said, this is gonna be the material of the sphere or the object in general. Spheres material. Okie dokie. So we have the spheres that are, I'm gonna zoom that in so you can see. We have spheres that are lit, obviously, and our light is somewhere, and they seem to be working fine with Phong. We have the specular, we have the diffuse component, and there's also some shininess to it. They are, in general, pretty diffuse. The material itself, it seems, and then we can work with this. They're fine. The thing I would also like to do, since I did that in this implementation, I also tried moving the lights a bit with my mouse, so I can tweak how the light actually, so I can see how the light actually bounces off objects, so I can debug stuff, as I had, of course, problems while I implemented it. I found tons of problems with the things I was doing, so this helped me a lot. And for you, when you're debugging stuff, you can't place a debugging point here and break it and do stuff like that. The way you do it, you just output different colors or different values as colors, as intensity or something like that. You always do something like that to see what's actually breaking. And we might actually do a debugging session at some point. I think it might be useful for you to kind of see when you fall into problems with this, it's quite hard to understand what's happening sometimes. So the thing we're doing here, we're just going to take the light, or the only light we have, and every time I move my mouse, when I click up and down or left and right, I will move the mouse, the light position, so it goes closer, or actually goes towards the z-axis, towards the screen, or back, and it can go left and right as well. Nothing spectacular, I just want to get some angles if I want to debug stuff. So this is how it looks like. So when I go like this, it looks like this. When I go like this, it looks like this. Let me see, when my mouse position on the y coordinate is Yeah, okay. Now I remembered when I saw this. At first point, I was a bit worried because it looked like we had a bug. But yes, I added one thing to this implementation in the meantime, which is the light intensity. And I don't think we had that in the previous tutorials. And this is pretty cool, the intensity itself, because as you know, in real life, when you have lights around you, their intensity drops with distance, right? So you're not going to have the same intensity while you're basically looking towards the lamp like this, and when the lamp is 100 meters away. It's completely different, right? Same thing here. If your light is further away from the object, it should not be that intense on them. It should be far less intense, and that's what happens here. And the formula for this, we can again Google it. Light intensity and distance formula. Yes, that's the thing. And as you can see, I already visited this page probably many times so far. So how do I calculate this? How do I calculate the intensity here? Oh, we go back to this formula and I say something like 0.1 squared divided by length of the light vector. That's the distance between the surface point position, one of the points position of this sphere towards the light, which is basically how far your light is from your object, pretty much. That squared times point light dot intensity, and it's, when you look at the formula, that is basically like taking, since we're trying to get, obviously we're trying to get light intensity on point 2, it's just doing the basic math. So I say I2 equals d1 squared divided by d2 squared times intensity on the point, on the first point, or intensity at the first distance. So here, when I say that my light intensity over here is 15, that means that that's the intensity on a distance of 0.1 in of unit length in this my tiny world. So that means that I know that the intensity is this big on this point, but that also dictates how intense will it be on each other distance by using this inverse square law formula for the light. So yeah, go here and check it out. And I also mentioned earlier this page, Scratch a Pixel, definitely super useful. Go here, read through as much as you can. This thing is like a Bible of basic ray tracing, and if you go through this thing over here, you will know a lot in the end to do lots of crazy things. So I found this to be quite useful, and every time I wanted to remember something or remind myself about something, I would go here. And another thing I'm gonna show you, which you also gotta have, in my honest opinion, is this. I don't know if my camera is of course inversed. Why wouldn't it be, right? But I'll write in the description below what the name of this book is if you can't read the reversed style thing. But you're smart enough, you'll figure it out. Anyway, it's 3D Math Premiere for graphics and game development. And this thing is the Bible. So it was, you can see that it was written with a lot of knowledge and passion. And it contains all of the basic things you gotta know, starting from basic intersections, how you intersect, I don't know, array and a sphere, array and something else, whatever, all the shapes possible, pretty much, all the primitive shapes possible, rotations, projections, stuff like that. I definitely warmly recommend it to anyone who wants to learn how computer graphics work. So let's go back to our model. We know the intensity. So the intensity of the light drops with the square of the distance, and this is what this line does in our new ray tracer. We don't need to go into too much depth for it, it should be basic math. So this was added to the Fonk shading model. So it is exactly the same shading model we used before in the previous ray tracer we did, but it has light intensity to it. And that's pretty much it. So we have nothing else to explain over here. And I think, okay, we have the spheres. So the thing we need to do now, we want to add the plane. And again, let's do it the way I just taught you, since that's the way you will probably be doing it and reminding yourself. So the first option is you open this book to remember, oh, how do I intersect with a plane? The second option is like, yeah, I remember how to intersect with a plane because I did it a million times before. And the third option is I'm just going to Google it. And in that third option, you'll probably stumble upon this brilliant page. And here, let's try searching for plane. Is it this one? I'm not sure. It could be. Let's see. Oh, we have some things over here. Ray plane and ray disk intersection. That sounds quite promising. Ah, yeah, exactly. This is what we need. So we have a ray, which is our ray direction towards the object from the camera, and then we have a plane. We want to make walls around this. If I show you the not the final implementation, but the current state of the implementation of what we want to do is this one. So we want to have these walls, and currently we don't have the walls, right? Awesome. Let's add the walls. Planes are infinite, obviously. They extend infinitely. And we're going to be using in our calculations a so-called denominator to kind of say, yeah, I can stop kind of intersecting with this plane at this point, or else it wouldn't be, I mean, it would work, but it's smart to do the denominator part because reasons. You'll see why in just a moment. But basically, a plane is defined by a point that should lie in this surface, in the plane surface, and it's called P0 in this notation. And then we have the normal that comes out of the plane that defines the angle pretty much. So with those two, you have defined a plane. If you only have, let's say, a point, you have a point. You don't know how the plane is turned in space. You have no idea what the rotation is pretty much. With normal, you do have a rotation. You kind of have a plane, but in theory, if it lied in the origin, yes, the normal might be enough. But since it can be displaced anywhere in space, like our walls definitely are, you gotta have a point that actually lies on the plane. The identity, of course, that is being used here to start the whole untangling of how it works is that the dot product of two perpendicular vectors is always 0. So we're going to be using that identity to actually figure out the rest of the equation. So here, the things you also see on this picture, this is in this photo, I don't know, it's L or Y. It's usually I means incident ray, the ray that goes in. So I thought it was I in this rotation, but it seems that the notation they use here it looks more like L, like small L letter. So I'm gonna keep saying L, but it should probably be I. And you're gonna see I as an incident and R as reflected ray. Pretty much in most notations online. But anyway, this is the origin of it, right? This is our camera position. This is the ray that shoots towards the plane that's somewhere in space. This I or L is the direction. This is our view, all the ray direction we already have in our implementation. Cool, we have this, we have this. This point over here, that's something we don't have. We don't have it simply because this point is the point where we hit the plane, and we have no idea of knowing that. We're trying to figure that out just now. So this is a big question mark. We have this one because we're going to define our plane with this point, and we have this one because we're going to define our plane with this normal. So before going and proceeding further, we can just paste the plane code I have over here that defines the plane with the normal, with the point, and I also added the color, and I also added the material. So we can, with that material, we can actually make it render slightly differently if we want to. So let me see where the plane is. The plane is there. Here. I also put the define planes count over here, so it's easier to loop through them. We can do the same for spheres later on. And let's define, for now, let's define one plane. This. So we do it in the same way as we did for all of the rest, and I'm using material 2, which we also define over here, which is slightly different. I think the ambience is, or no, the shininess seems to be slightly different here. I just took whatever worked for me in that scenario. You can put the numbers and colors you want that look good for you. So this compiled, that's pretty good. And we gotta start adding stuff. The plane itself, just to map to the things we just talked about a second ago, the plane is defined by a position, which is a point on it, normal, and we'll set a color and material. Cool. Let's go back here to figure out how we do the intersection part. That's the most important part. So first we say any point on the plane, right, which is P, which we don't know, minus P0. So we have a vector that goes this way, right? That vector should always be perpendicular to n. That's logical. Every point on this plane lies in the same 2D surface, and it always, whatever vector you get on that surface, it always needs to be perpendicular to the surface normal. So we use that to kind of hack our way through this formula. Similarly, if you take this, which we call L0 in this case, if you take this point, and if you take the direction and multiply it by t, t is the distance from this to this, basically. If you multiply the direction with distance, direction is of course normalized, you multiply it with distance, you basically get the vector that goes from I0 to P0, or to P, I'm sorry, yes, to P. And when you have I0 plus that vector, that gives you the P position, because that's the absolute 3D position of this point P. And that's the parametric form of this point. And now, it's kind of similar what we did with the sphere. So you just put one formula into the other, and you use this formula over here and put this P over here. And when you do this, you get this term over here, this equation over here. L0 plus L times T, which is the P, minus P0, obviously. And you do dot product n equals 0, because we have this identity that they are perpendicular to each other and it should be 0. Cool. So we learned that as well. Now, when we do some shuffling and we manage to extract the T part, because obviously we want to get the T part, because if we have T, we have P, because we have the rest, right? And T is going to be the distance that we're going to be using for other things as well. So when you finish with doing math here, the formula you get is that T equals P0 minus L0, all of that dot product n, divided by L dot product n. Final formula, which is actually quite simple. And then when you just moved into the code part, you basically do that. You take the dot product of n and L, which is the thing you see here, which is also called denominator, and I'm going to be talking about that in just a few moments when we start coding. That denominator, by the way, let's go here just so you also grasp that part. L is this one, N is this part. If you do dot product between them, if the dot product is negative, that means that you actually see the plane, right? If it's positive, you don't see the plane because you're heading in the same direction. And planes, actually, when you deal with planes, you can make them render both sides if you want to. In my case here in this ray tracer, no, we're gonna do them only if the normal of the plane is heading in the opposite direction from my incident ray. So this dot product tells you, oh, can I even see the plane? It's like a normal thing we did with the sphere, like. And this denominator is here just because if you have a normal, let's do this. So if you have the normal, and let's say you have a plane somewhere in space. Can I get the rectangle? Yes, thank you. Let's say you have, it's gonna be a super simple drawing, but let's say your camera is over here, and let's say that this plane stretches in space. So when you hit this plane somewhere here, you can see it, right? If your direction extends slightly differently, like this, you can actually still see it, because what planes are, guess what, infinite. So in theory, you can see it to the half your screen always, and that makes it kind of tricky because you don't want to render the whole thing until the end of the universe almost. Like you don't want to do that, right? You want to clip it somewhere and you want to stop the calculation somewhere and say, yeah, I don't want to render it, I don't see it anymore, right? The thing is, as it goes infinitely, when it goes infinitely, at some point your direction can be something like this and you can still see it because it's somewhere there. And the denominator part tells you, well, if you are if you are on this value, just stop drawing it, stop intersecting with it. I don't want to intersect with it right now. And you can put that number to any number, and we'll play with the numbers so you can see how that affects it. But that's what this denominator is, and that's why we had 10 to the power minus 6, because that's like a small number, but it gives you some margin where you say, yes, I don't see this thing anymore here. And with this margin, you just continue for. This is pretty much like saying, yeah, this denominator is, yeah, I can see the plane pretty much. And then there's P0, L0. P0, L0 is P0 minus L0, which is this vector over here. And we need it because in the formula it's over here. And with P0, L0, we have all the parts of the equation we need. And we say, well, T is obviously dot product of P0, L0 and N. So we get this part. And we divide it by the denominator, which is L dot product N. And then we return if T is actually larger or equal to 0. And if the distance is larger or equal to 0, that means that you see the plane somewhere in front of you on some distance. That's kind of the simplistic explanation of this point. Again, I definitely recommend you check out this page. There's a lot of other pages on the internet, but this one is pretty simple. And we now need to do the intersection part. I will just copy the code that I wrote for the new one, and it's actually identical, or yeah, it's mostly identical to this code over here. I kept it almost the same, so you can map it easily to this one. Once you read through it again, you'll know what which part is what. I kept the notation the same, so you can also map the notation to the image. It's much easier. So we do the math as we did before. You'll notice one difference though. I said here, well, the denominator needs to be less than 10 to the power minus 6. The reason is simple in our case over here, and I don't know if this is on purpose over here. Maybe the things they're sending here or all the setup is different, but basically you need to have a dot product that's negative to be able to say, yes, I can finally see this object over here. So this is the only thing that's different in our case. Let's write another for loop for the planes. Like this. And we can do this. Planes count. Is it plane count? Planes count. Planes count. Cool. And then we're gonna intersect, or actually we can't copy that part that easily, but we're gonna do intersect plane. And now we need to pass the plane to it. Obviously it's gonna be planes and I. And then we need the origin, which is going to be ray origin. And then we need the ray direction. And then hit distance, which is the distance. Cool. If you manage to hit that, final color equals get lit color. Basically, we do the same thing. So we have the same function call for getting lit colors for both spheres and planes. Did we define a plane? It seems like we did. We don't see it, probably because we forgot something. Let me see, planes. Yes, I think I forgot to actually set this plane on the planes. So inside of the setup scene, we're gonna have spheres, we're gonna have planes. Planes 0 equals plane 1. We have the plane. And now we have something interesting. We have a plane that's doing something weird to the sphere, and then the sphere is also taking some weird color over here. Like you already see that something definitely went wrong with this, right? Let's see first here. First we see that the sphere's color we're passing. If you do this, we get the planes. But look at this now. What's happening? Well, let's do this. I'll give you a minute to figure out what's happening over here. I'm just gonna say we're missing one big chunk of, not big chunk, but we're missing one part of logic to be able to render this properly. So if you want to tackle it on your own, pause the video now, and as soon as you're done, unpause it and let's see.
A few moments later.
Hopefully you paused it and tried on your own. If you didn't, it's fine. We're gonna tackle it together. The thing that was missing is distance calculation, because right now what we are rendering, we are fiddling with this final color over here, then we're fiddling with this final color over here, then we're outputting a final color. But in all of that madness, we forgot the fact that the distance is not accounted for. If you have an object that's behind this sphere over here, you have no way of knowing. You're actually outputting the color of whatever you see or intersect with last over here, and you can't do that really. So the thing you need to do to make this thing work, you need to take the distance and have the distance tracked all the time, and always render the thing that's the closest to the camera. Of course, that's what we do in one pass of the ray tracing, and you'll see when we do multiple passes we'll actually go all over the place. But to start with this thing, we're gonna do one cheat, and look at this math crime. So when we do this, we produce infinite result on the distance. We want to do this because we want to start the loop with a maximum distance possible, so something that's infinitely distant to us. And when we do this, here when we compare the distance we get over here with the distance you have here, this should be the absolute distance of the object you see. It needs to be less than this distance. So for the sphere, we're gonna say maybe we have this sphere hit distance. Let's make it like this, and we can change it later. Sphere hit distance, and then we pass it over here, and then this is the distance that's going to be set by the sphere, and then you need to compare it with this distance to get the color. So we're gonna say, well, if sphere hit distance is less than distance, then do this. Cool. So it's still not doing anything because we are still missing a part of the equation. Let me see, sphere hit distance equals less than distance. Yes, we're also missing one part of logic here. Obviously the closest distance to us right now is this sphere hit distance, so we do this. Okay, and then let's do the same for the planes. Maybe we can name this object hit distance, because we don't really, I don't think we care about which objects. This one as well. Awesome. And then we're gonna do the same thing here. So this one calculates the distance here. Do this. And then we're gonna say distance equals object hit distance. Okay, finally, one thing I also don't like having this like this. Cool. Yes, now you can see this. The thing I noticed immediately is the fact that our plane is not super reactive to the light, and it seems that it's because the spheres might be the sphere's material. So we're gonna do plane's material, and I'm not sure if I'm setting the material correctly. I'm doing it actually correctly. It might be that the color is the same. I don't think so. Let's check it out again. Planes material, planes dot material. Did I name it material? I did. And when I start it up, I have this material 2. Do I do the same thing for the sphere? Material 2 material. Why is sphere 2 and material 2? I want to have them the same material, and then I want to have planes different. But what if I do this? I get something. Okay, that's interesting. Material 1 works. Material 2 does it. It could be something wrong with the setup over here, although I really doubt. Let's debug stuff together. If we have material 2 over here, we set it on the plane. The plane is defined here, and it's interesting. Material 2. Let's try copying the same parameters and seeing if that works. This is super weird. Okay, yeah, seems to be working in this case. Get lit color. What if I return different final color in the ray trace? So it. Okay, yeah, it's definitely drawing something. Although, to be frank, it looks quite dark. I wouldn't expect it to be this dark, although it might be the thing. Maybe we could change the color of the floor. I think I put the... Yeah, let's put this one also to be a bit bluish, like I had in the example, just to see how it reacts. It looks quite dark. Now it's super weird. Okay, let's see what other parameters we have. So we have this one. Oh yes. Okay, this is a problem. So p hit we're passing over here is actually the p hit calculated by the sphere. So this is not gonna work. We gotta work with the different p hit. So the intersect function of the sphere doesn't have a p hit that's being returned right now. So we might want to do that as well. So let's take this intersect plane and let's do out vector 3 p hit, and the notation I'm using here is like this, but let's change it because I changed it everywhere. I don't know why I put it capital P to start, but it might be the notation I found. Okay, and this p hit should return. It doesn't matter what it returns if there is no intersection, but we can put that the p hit equals vector 3 0 like this, and that seems to do the trick. And here, what's the p hit? Let's go back to this one, and again I'll give you a minute, pause, and figure out how can you get the p based on this thing over here.
A few moments later.
I hope you paused. If you haven't, again, I think that's fine. We can do it together. So we said that the p is this point, or actually this direction, multiplied by the distance, which is going to be t. So it's L or Y, or in our case L, times t plus L0, right? So it should be, do we have that sort of calculation already? We don't. So it should be vector 3 or p hit equals L0, which is gonna be the origin, plus the direction. But wait, what's our redirection? Yes, it's that direction. Times t. That's a y. But I put hit distance over here. Maybe we should, if we're using t, I'm gonna put t here as well for your convenience inside of this function. And then we're gonna go here. We're gonna pass the p hit here. And then this one should be writing to the p hit position right now. Let's see if we did it correctly. Origin plus redirection times t. Okay. And that should do the trick. If the object hit distance less than, it still doesn't react to this. Surface normal, that's also something to be worried about. Surface normal, get lit color. Okay, so we're passing the surface normal, but the surface normal is again something we don't have in this case. The surface normal is actually the normal of the plane. Because we don't calculate, so we can just do okay, and now we're getting somewhere. Let's start adding stuff. I will also put the I'll put the color that we see in the background to something a bit more eye friendly, so we don't get blind altogether. It should be in the ray trace where we set the final color, so we'll put something a bit bluish. Yeah, this is horrible. Let's just do something like that for now. We're gonna be adding planes now. So we have this plane, so good job so far. It seems to be working fine. Let's also, since we have planes count, let's do spheres count. And let's define the spheres count here. Like this. And we can define them as 2. That compiles, that's good. Let's see. We want to add the others, the other planes. Right now, obviously, we don't have any but this one, so we can just keep adding them. Or actually, since I have the positions already set in stone over here, it's better if I just paste them, and then we can potentially discuss them, but I don't see a need for it, to be frank, because it seems to be quite straightforward. It should be straightforward for you at this point. Okay, and now we have a situation because I didn't do this. You could also, I mean, you can do this in a loop if you want to. Okay. And now when your light is super far, when I go down, it's a bit dark and weird. If you go like this, you can see the room. In my previous implementation over here, the floor is of different colors, so we could do that as well. If you don't like the colors, change them. This is something that I just did randomly, and for me it worked okay-ish. Let's see where the plain color is. This one. Yes, there we go. And we have something now. To proceed further, by the way, just to kind of quickly explain, the positioning of the planes, you can see that we have one on the left, one on the right, one on the top, we have one in the back. You define that by positioning and normals, of course. And there's also one plane behind the camera, because when we do reflections now, you'll actually see nothing behind. You'll see this gray color we set. So I'm preparing the field for proper things. I think we should now tackle shadows maybe, and then as the like a last point, I would like to tackle the loop, the ray tracing loop we're gonna put in place, so we can actually bounce as many rays in as many loops as possible, and that then unlocks the full potential of this ray tracer, and that's the reason why we switched it. Also, I think this tutorial was more of a conversational one, going a bit back and forth. Let me know down in the comments if you'd like this approach where I slowly go through things, and where I also debug things as I go. Let me know if you like this more, or you like where I actually just kind of go with script and go step by step. But I think this approach is better. It gives you a more humane approach, and this is when you implement stuff, it never goes straightforward as you might think so. So looking at watching someone who's doing it scripted is fake. That's really bad acting then. So when you're doing these things, you will stumble upon many problems as you go. You might have a lot of bugs along the way, and that's fine as long as you're learning from each of those mistakes and progressing further. That's super good. Just keep doing it. So yeah, let me know now down in the comments.